Hi there, folks. Today we are going to be covering section 4.6, Antiderivatives. Now notice that it is a single section, and that is because it is one of the more important sections, and so I want to make sure that we really have a focus on it. There are really two main concepts in calculus, derivatives and integrals. And the antiderivative is another name for one of the types of integrals. And that's what we're going to be focusing on today. But first, let's make sure that we know what we know. And so we started with limits and continuity, but then we learned derivatives. And we know derivatives. At this point, we should be very comfortable with derivatives. Their slope, the rate of change, their velocity, they're coming from the difference quotient idea. They are based on limits. I mean, we can take the derivative of just about any function and they are very, very nice. Integrals are different. And so there's two forms. One is the indefinite integral, which is what we'll be learning today, and is also known as the antiderivative. And the second is definite integrals, which I believe we'll be learning in our next lesson. And so that's coming. Integrals are tricky. And so there's a number of applications for integrals because what they do is they undo a derivative. And so if you know the velocity, this will tell you the position. If you know how something is changing, this will tell you the values that you would have for something. If you know how a population is changing, for example, the antiderivative will tell you what the population actually is at a particular time. It's a way of undoing a derivative. And I put in here that it's kind of like the relationship between FOIL and factoring. And so foiling is fairly easy. We can FOIL no problem. First, outer, inner, last. And whenever we're multiplying two binomials, we get a solution. Factoring, though, can be trickier. And if we have four terms, we might not be able to factor it very nicely. It might not factor at all. And that can be tricky. The same goes for derivatives and antiderivatives. One of the common analogies which is used to describe them is the idea of Fred Astaire and Ginger Rogers. It used to be a big question of who was the greatest dancer in the world. And back then, everyone would always point to Fred Astaire. And they would say, well, Fred Astaire is an amazing dancer. But he would always be dancing with Ginger Rogers. And so the adage always went that Ginger Rogers was the better dancer, because she would have to do everything Fred Astaire did, but backwards and in high heels. That's kind of like the antiderivative. Antiderivatives are like derivatives, but doing them backwards and in high heels. They can be very, very difficult. Sometimes they will be impossible. Sometimes even the simplest ones, the simplest functions that we know, we will be unable to find the antiderivative for. The entirety of statistics is based on a single antiderivative, which we're unable to do. And so these can become very, very tricky. Today, we're just going to be learning the fundamentals. Chapter 5 goes more in depth into how to actually calculate antiderivatives when they're a little bit more complicated. But today, we just want to make sure that we have the antiderivative fundamentals. And so let's start with our definition. And so a function, big F, you'll see this notation fairly often where we use big F and little f. Be aware that big F and little f are representing different functions. And so a function, big F, is called an antiderivative or an indefinite integral of little f on an interval if big F prime is equal to little f for all x on the interval. Given a function, the antiderivative is the function which has a derivative which is your starting function. That can be complicated to wrap your head around. And so I have an example real quick, just so that we can understand it. And so the function big F equals 3x squared plus 2x plus 4 is an antiderivative of little f is equal to 6x plus 2, because the derivative of big F is little f. And so if we were to take the derivative of this function here, 3x squared plus 2x plus 4, we would get 6x plus 2. And notice that's what 6x plus 2 is over here. And so this function would be called the antiderivative of this function, in much the same way that we would say little f of x is the derivative of big F. One thing to note, though, is that this is not the only antiderivative. If we were to use this function, g of x, which is 3x squared plus 2x plus 7, this is also an antiderivative, because if we took the derivative of it, we would get 6x plus 2. In general, any function of the form f of x, or big F of x, equals 3x squared plus 2x plus c will also be an antiderivative. This c could be any number. And so c could be 7, it could be negative 1 million, it could be pi. It does not matter. If we took the derivative of this, we would get 6x plus 2. And so anything of this format would be considered an antiderivative. As such, whenever we find the antiderivatives, we will always include a plus c term. That makes it so that this is the general antiderivative, or general indefinite integral. There's an uncountably infinite number of antiderivatives, but they will always be of this form. And so when we write the antiderivative, we will always write it in this format, where we have the plus c value included. And just to make that clear, always, 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 always include the plus c. Whenever you take an antiderivative, you should have a plus c term at the end. Note, this is only for indefinite integrals. Once we get to definite integrals next chapter, we'll be dealing with different stuff. But if we're talking about the antiderivative or indefinite integral, we always have plus c. Now, because having a big F and little f can get confusing, we have a notation for this. And so if an antiderivative of little f is big F, then the process of integrating the function can be written this way. The integral of little f of x dx is equal to big F of x plus c. This symbol is called the integral sign, and it's kind of like a stretched S almost. You can see that it starts curving downward, and then it goes flat, and then it curves upward at the bottom. We will also always have this dx at the end. And for now, we don't need to stress what that dx actually represents. Really, what this is saying, for our purposes for now, is we're going to find the antiderivative of whatever is between this integral symbol and this dx. And it could be other variables. It could be a function with respect to t, and then it would be dt. Or it could be a function with respect to u, and then it would be du. We have to have this term at the end. And again, we won't stress what that represents quite yet. That'll be next chapter. The function f of x, this inside part, is called the integrand. And yeah, like I said, for now, we're not going to stress what the integral symbol or the dx means. Once we get to Riemann sums next chapter, we will. And with that, let's just practice a whole bunch of problems to make sure that we understand how to do these. And so I have 20 problems here. We're going to go through all 20 of these. And so if you want, pause the video now and try and go through them. Once you do that, we will see if we can go through every single one of them. Or you can work through them as we're going. And so I will stop the share, and we will just start working on them one at a time. And we'll begin with number 1. The integral of 2x dx. And so what we're looking for is we're looking for a function which has 2x as its derivative. And it might take some thinking. Right now, this is a line, it's 2x. And so what function, if you took the derivative of it, would give you a 2x? In this case, it's going to be x squared. And let's see why that is. If we take the derivative of x squared, we would get the 2 that comes down, and it would become 2x plus c. And so we kind of want to use this backwards logic. The best way that I tend to think about it is I kind of think of it like a guess and check at first until you start to get more familiar with them. There are a lot of rules which will help you as you go along, but if you can try and understand them using a guess and check approach for now, it'll make it so that it's a little bit easier to understand why the rules exist as we go on. And so for the next one, the integral of 4x cubed minus 17x to the 16th dx. And so 4x cubed, seeing an x cubed, if we were to take a derivative of an x cubed, it would become an x squared, and we would have the 3 come down in front. Well, we want to do the opposite of that. And so instead of subtracting by 1, we're going to be adding 1 to that exponent. And so we would get an x to the 4th. And now let's check. If we took the derivative of x to the 4th, the 4 would come down. That's good. We'd be left with x cubed. That's perfect. For this one, same thing. If we were to take the derivative, we'd be subtracting the exponent by 1. But we're doing the antiderivative. And so we would want to add 1 to that exponent. And double checking the derivative of x to the 17th, the 17 would come down, give x to the 16th. Plus c. Number 3 is the integral of x to the 7th minus 3x to the 6th. So let's use the exact same logic. If we were to undo the x to the 7th, then we would add 1 to our exponent. We would get an x to the 8th. But notice that if we took the derivative of x to the 8th, we would get an 8 that comes down. And so we would expect 8x to the 7th. But we do not have an 8 here. In order to make it so that we don't have that 8 there, we need to cancel it out. We can cancel it with a 1/8. Because now when we take the derivative of this, the 8 would come down and we'd get 8 over 8, which is just 1. And then we'd have x to the 7th. Same for this one. And so we would be adding 1 to that exponent, giving us an x to the 7th. But when we took the derivative of x to the 7th, we would expect a 7 to come down. And there's no 7, there's a 3 there instead. So somehow we need to get a 3 out of it, and we need to cancel that 7 out. And 3/7 will do that, because the 7 would come down and cancel, and then we would be left with a 3. Let's see. 4. The integral of x to the 19th plus 2x to the 20th. Same idea. And so we would add 1 to that exponent, giving us an x to the 20th, but then we would need to cancel it out with a 1/20th. And then for this one, it would go to an x to the 21st, and we would need a 2/21 to cancel it out. And double check. When you take the derivative of this, the 20 comes down, you get x to the 19th. The 21 comes down, you get 2x to the 20th. And the derivative of c just goes to 0. Five's trickier. And so the integral of the square root of x plus the cube root of x squared dx. Instead of doing this one directly, what I would recommend is you rewrite this as a fractional exponent. Because if you rewrite these two terms with fractional exponents, you'll be able to just do the antiderivative using the general power rule. And so rewrite this as the integral of x to the 1/2 plus x to the 2/3 and then just like with all of these before, we're just adding 1 to the exponent and then figuring out what we need to cancel it. And so adding 1 to 1/2 would give us 3/2. But there's no coefficient here. And so when we took the derivative of this, a 3/2 would come down. To cancel it, we would need a 2/3. Because now the 3/2 comes down and it cancels. X to the 2/3, again, we're going to add 1 to it. X to the, that would be 5/3. Which means we need a 3/5 plus C. So all of these have been using the same power rule, which is kind of nice. The next one, well, it's a little bit trickier. And so for 6, the integral of 1 over square root of x plus 1 over x squared plus 1 over x. If it helps, you could rewrite these as fractional exponents again, or negative exponents as the case may be, in which case this would become the integral of x to the negative 1/2 plus x to the negative 2 plus x to the negative 1. But what I find interesting about this one is the answer for all three of these looks very different. Because when we add 1/2, or when we add 1 to this, we will get x to the 1/2. And then to cancel that out, we would need a 2. For this one, when we add 1 to negative 2, we would get a negative 1. And to cancel a negative 1 out, we would need a negative. But the really tricky one is the x to the negative 1. Now, often people will say, well, just like all of these before, we would add 1 to this and get x to the 0. And then we would need a 1 over 0 in the front, and we can see that things go horribly wrong. The reason for that is we're not going to get a nice power out of the 1 over x term. What function has a derivative which is 1 over x? And that's the natural log. And so our answer, if we wanted to write it out in a cleaner version, would be 2 square root of x minus 1 over x plus the natural log of absolute value of x plus c. Now, this absolute value, it doesn't actually matter for this problem because the domain's restricted by that square root. But the reason we put the square or the absolute value around the x inside of the natural log is because the natural log is going to be the antiderivative, whether or not the x value in 1 over x is positive or negative. And so the absolute value makes it so that natural log is defined for both positive and negative values of x. And so that's why whenever we're doing the antiderivative of 1 over x, you should write it as the natural log of absolute value of x. Again, for some problems, domain may modify that, but in general, you will want to put that absolute value there. Number 7. Integral of e to the t. What function has a derivative which is e to the t? And it's just e to the t plus c. For 8, e to the 2t. Well, we know that if we took the derivative of e to the 2t, we would get an e to the 2t and a 2. And so the e to the 2t should still be there. But like I said, when we take the derivative of this, we would get a 2 that comes out. And to cancel that 2 out, we'll place a 1/2 plus c. Nine is the integral of 2 to the t. And so similarly to the e to the 2t, when we take the derivative of 2 to the t, we know we get a 2 to the t times natural log of 2. And so we should expect a 2 to the t here. But taking the derivative of this would get a natural log of 2 to come out, and we don't have a natural log of 2. And so we balance it with a 1 over natural log of 2. And it doesn't matter what the function is. If we have something like 3 pi to the t, well, pi is just a number. 3 in this case is just a scalar. If you ever have a scalar, you could technically just factor it out. And so this would give us a 3. The pi to the t is still going to be there. But when we take the derivative of pi to the t, we would get a natural log of pi that comes out. So to cancel it out, we would divide by a natural log of pi. Plus c. All right. The next 6 look like they are our trigonometric ones. So let's make sure we know our trig functions. All right, number 11. 11 is saying the integral of sine of x. Well, we know that sine goes to cosine and cosine goes to negative sine when we're talking about derivatives. And they just go back and forth. And so we would expect a cosine term here. But the question is it positive or negative? And we can check. If we take the derivative of cosine, we would expect to get a negative sign. And so to balance that out, we will throw another negative in, because a negative times a negative is a positive. Plus c. 12, the integral of cosine of x. Well, again, cosine goes to sine, sine goes to cosine. And so we would expect a sine of x. Again, the question is it positive or negative? The derivative of sine is positive cosine, so the signs are good. (13) is the integral of secant squared of x. The integral of secant squared of x, well, what function has a derivative which is secant squared? And that is our tangent. 14, the integral of cosecant squared. Well, what function has a derivative which is cosecant squared? And it's almost cotangent. But cotangent would get a negative sign that comes out. So to balance it, we need to throw a minus sign in there. Because again, a negative times a negative would give you that positive. 15, the integral of secant x tangent x. Well, secant x tangent x is the derivative of secant. And then same goes for cosecant cotangent. Oh, and I forgot my dx on that one, for shame. So the integral of cosecant cotangent, well, it's almost going to be cosecant, but we would be missing the minus sign. Plus C. (17, 18, 19, and 20 are a little bit trickier, but not a lot trickier. So let's work through them real quick. And so 17 is the integral of 3 times 5 to the t minus cosine of t dt. And with this one, we can just do the two parts separately. And so 3 times 5 to the t, well, we know that the 3 times 5 to the t is going to have that 5 to the t there. We're going to have the 3, and we're going to need to balance it with a natural log of 5. For the cosine function, we know the antiderivative of cosine is just sine. And so the minus sign will just hang out. Plus c. And if you want, double check, derivative of 5 to the t would be a natural log of 5 times 5 to the t. Natural log of 5s would cancel out, and you'd be left with that 3 in the front. 18. Oh, 18 is a fun one. Integral of d dt of e to the tangent of t dt. And so this is saying, what's the antiderivative of the derivative of this function? Well, the antiderivative of a derivative is just going to cancel one another out. And so we would get e to the tangent of t plus c. (19) the integral of 7 dt. Well, 7 is just a number, and that would mean that the antiderivative, the 7 would be the slope of a line. And so this is going to give us 7t plus c. And our last one is the integral of 0 dt. Well, the integral of 0, what function has a derivative which is 0? And that's just any constant. And so it's just c. And so those are those 20 introductory problems. And for the most part today, we just want to introduce this idea of the antiderivative. Let's work through an application real quick, though. And this is a rocket science application. And if you want, I do have the answer written down here. But this is kind of a fun one because it introduces how we can start to think about the antiderivatives. And so if h of t is the height of an object at time t, then h prime of t is equal to v of t, which is the velocity. And so we have position and we have velocity. H double prime of t would be v prime of t, would be a of t, which would be the acceleration of the object. An acceleration we can often think of in terms of gravity. And so looking at this problem, it says the gravity or acceleration on the moon is 5.315 feet per second squared. And that would be pointed down, so really it should be a negative 5.315. If Buzz Aldrin fired a spear gun, which has an initial velocity of 100 feet per second directly away from the moon, from an elevation of 80 feet above the lunar surface, how long would it take for the spear to hit the moon? And we can figure this out. And so let's draw a quick model I'm going to have the lunar surface. So we'll say the moon. We're going to draw a picture of Buzz Aldrin with his spear gun. And then we see that he starts out 80 feet it was, I think. Yes, 80 feet. And then we have the spear is going up at a velocity of 100 feet per second. And then the gravity of the moon is negative 5.315 feet per second squared. And we want to know when it's going to hit the moon. And so here is our interesting little model. Well, thinking of this in terms of height, velocity, and acceleration, we have some good information. The negative 5.315 corresponds to the acceleration. And so A of t is a fixed thing. In reality, I believe gravity is tied to distance as well as mass and a whole bunch of other stuff, but we can treat it as constant for our purposes. And so A of t is going to be negative 5.315. The 80 corresponds to our initial height. So h of 0 is equal to 80. And then our velocity, our initial velocity, is going to be equal to 100. Now remember, this A of t also corresponds to v prime of t, which also corresponds to h double prime of t. And if we want to know when it's going to hit the moon, then our goal is to figure out when h of t is equal to 0. And so when is h of t equal to 0? And so in order to solve this, we can use our antiderivatives. And so we start with our acceleration function. And so A of t is equal to negative 5.315. In order to find the velocity, v of t, we would need to find the antiderivative. And the antiderivative, well, the antiderivative of negative 5.315 would be negative 5.315t plus c. We'll call it c1 for now. In order to figure out what the c1 is, well, technically it's going to be v of 0, but if we didn't know that, we could actually plug v of 0 equals 100 into this equation. And that would give us that 100 is equal to negative 5.315 times 0 plus c1. So c1 is going to be equal to 100, since that term goes away. Well, now we have our velocity, v of t, is equal to negative 5.315 t plus 100. In order to figure out our h function, we have to take the antiderivative of this. The antiderivative of this, well, this t is going to become a t squared. But because it's a t squared, the 2 would typically come down, and so we need something to cancel it. The antiderivative of 100 would become 100t. And then we're going to have a new constant. So we'll call this one c2. And now we got to figure out what C2 is. Odds are it's going to be our 80. But if we're not sure, we can check, because we would say that 80, oh, and I'll indent this a little bit like I did before. So 80 is equal to negative 5.315 over 2 times 0 squared plus 100 times 0 plus C2. And so C2 is 80. So that means that our h of t function is going to be equal to negative 5.315 over 2 plus 100. Oh, I forgot my t squared. T squared plus 100t plus r80. And the question we were asked is, when is that going to be equal to 0? We can solve this. This is a quadratic. And so from here, we would use the quadratic formula. You could try and factor it if you were really excited about that, but I wouldn't recommend it. And I got a feeling that after you use the quadratic formula, you'll get 38.413 seconds out of it. Technically, you'll get 2 answers. One of them will be negative and won't make sense. The other one will be this positive answer. And hopefully this is the correct answer, because this is the answer that I have in the notes. And so do the quick share screen. Yeah. And so double check that number. Use the quadratic formula and see if you get 38.413 out of it. If not, well, we can leave something in the comments. And so that's an example of a very traditional physics problem that you might see. Yeah, it's very introductory from a physics perspective. For us, we're more into the biology and medicine. And so you're probably not going to see many rocket science applications. Instead, what you're going to be told is you're going to be told the rate of change or the acceleration of a bacteria colony or something like that. The process for finding the population at a particular time is going to be the exact same. You're going to have to use your antiderivative. Now, here are some antiderivative formulas, and one of them is incorrect because I was bad when I wrote this. See if you can spot the incorrect one right now before I give it away. But looking through this, we have the sum. And so if we're taking the antiderivative of the sum, it's just going to be the sum of the antiderivatives. We still have the scalar rule. And then we also have our power rule from before. We know the integral of 1 over x is the natural log of x. Integral of e to the x is e to the x. Integral of a to the x is 1 over natural log of a to the x. And now we're getting into the one which is wrong, because the integral of sine of x is going to be negative cosine, but the integral of cosine is not negative sine. Sorry about that. Fix that in the notes. That should be a positive sine, because the derivative of sine is positive cosine. So that should not be there. I believe the rest are correct, though. And so secant squared goes to tangent, cosecant squared goes to negative cotangent, secant tangent goes to secant, and cosecant cotangent goes to negative cosecant. I put a note down here just to make it so that you feel a little bit better, because again, these can get very, very difficult. And so you're going to get derivatives and integrals mixed up for the next couple of weeks. You're going to get them mixed up for the next couple of months. And even once you have a master's degree in math, you will still get them mixed up on occasion. This is okay. It takes practice, but by the end of the term, you'll be able to take the derivative or antiderivative of anything I throw at you. And this is true. There are definitely going to be examples where you will make mistakes, because sometimes the answer will seem intuitive, but it's something which you'll have seen so many times and you will make those mistakes. Let me show you some examples. Some of the most common ones which people will mess up is when we're talking about things like this. ddx of natural log of x versus the integral of the natural log of x dx? And then how about d dx of 1 over x versus the integral of 1 over x dx? These four are the ones which people often mess up, and I'm guilty of it too. I'll occasionally get these mixed up in a moment. But let's look at them and why it's easy to mix them up. And so the derivative of natural log of x is going to be 1 over x. And that's the formula which we remember. The integral of natural log of x, we don't have that tool yet. We don't have a direct formula quite yet. Next chapter, we will develop those formulas. And so that's coming. But then when we see this 1 over x, the derivative of 1 over x, a lot of people automatically will say, oh, that's going to be our natural log of x. But it is not. The derivative of 1 over x is negative 1 over x squared. And you can do that using the general power rule. It's the antiderivative of 1 over x, which gives you your natural log of absolute value of x plus c. I would say that this 1 over x is the one which most people make the mistakes on. But there are others. I mean, you're going to get signs wrong when you're talking about sines and cosines. As you saw in the notes, I got that wrong when I was writing those notes about 5 years ago. And one of these days, I promise I will fix those lecture notes, but probably not today. It's okay for you to make mistakes on this stuff. And it's especially okay for you to make them now. This is the time when you want to make these mistakes. You don't want to make the mistakes when you are writing your dissertation and the mistake is at the beginning and you have to go and redo all of the math for your entire dissertation. Right now it's low stakes. And so make your mistakes now and make sure that you get very comfortable with this stuff so that you don't make the mistakes when it counts. And again, it's okay to make the mistakes. They will happen. The last thing we're going to talk about is introducing the idea of differential equations. I don't know if you've seen the pen talk yet. I might have to do that next. But differential equations are equations which include derivatives in them. And in order to solve them, you typically have to integrate. You have to do the antiderivative. I have a few examples here. I don't know that I want to do the fourth derivative one because that one's a little gross. But let's take a look at some of these. And so consider the following differential equations. These are pure time differential equations. And so this one is saying the rate of change of y with respect to t is equal to e to the t plus 0.16 t to the 9th. You may hear that there's an air show going on in the background. Sorry about that. And so for this one, let's just look at number 1. dy dt is equal to e to the t plus 0.16 t to the 9th. What makes this a pure time differential equation is that all of the variables on this side are t. And so they're all tied to the time variable. None of them are dealing with y. If we had something like a plus 3y here, it makes the problem much, much harder. But if it's just with t, then we can just take the antiderivative. And so the antiderivative on the left side is just going to give you y. On the right side, we would get integral of e to the t is e to the t. The integral of 0.16 t to the 9th, well, that's going to be a 0.16 t to the 10th divided by 10, which should give a 0.016 t to the 10th. And then we'll also have a plus c term. Now, one thing to note about this, this is the answer, by the way, but what we're doing is we're really integrating both sides with respect to t. And you might notice that when we integrate on the left side, we should get a plus c term on the left side as well, because we're integrating. So we should get a plus c here. Well, it turns out that the C value on the left side and the C value on the right side would typically be different C values. And if we subtracted it over, we could just combine them into a single variable C value. And so it's kind of like we had a plus C1 and a plus C2, and then we subtracted the C1 over, giving us C2 minus C1. But then we said, well, why not just call this C? And that's what this corresponding C is actually representing. And so you'll see this simplification of those constants happen quite a bit. But that's all you have to do a pure time differential equation. Let me write up the second one that we have, and then we'll skip 3 and 4 because they're kind of silly. 2 dy dx minus 1/4 x cubed equals 7 over x. Now this one's not dealing with time because it's dealing with x, which typically represents a spatial component. And so we would still call it a pure time differential equation, and the strategy would still be the same. Our first step is we'd want to move everything over to one side. And so we'll keep our dy dx over on the left side. And that would give us a 7 over x plus 1/4 x cubed. And now we would need to take the antiderivative. Well, we'll get y equals the antiderivative of 7 over x is going to be given a 7 natural log absolute value of x plus x to the 4th and a 1/16. So those are pure time differential equations. There's one more thing to show with these pure time differential equations, and that is the idea of an initial value problem. We'll save that note for later. An initial value problem is a type of differential equation that gives you information about a function and asks you to find a particular solution. And so if you are told a particular piece of information, like what the initial amount is, then we can use that to actually figure out what our C value is. And so let's do number 1. Number 2, again, is kind of silly, but number 1's a good one. And so for 1, it's dy dt is equal to 2e to the 3t minus 3. And the initial condition that we're given is we're told that y of 0 is equal to 1. And so this right here is the initial condition. And that's what makes this an initial value problem, because we're told that this is where we're starting. And if we're told a value with which we're starting, then we can actually calculate our C value out. And so let's figure this one out. dy dt equals this. So to solve for y, we would integrate. 2e to the 3t is going to give a 2/3 e to the 3t, because when we take the derivative, the 3 would come out and cancel, minus 3t plus c. And so this would be the general solution, because we haven't solved for c yet. But now we can solve for c using y of 0 equals 1. Because if y of 0 equals 1, that means we can plug the 1 in where our y is. And then our t value is 0. Be careful. This 1 value does not necessarily correspond to the c, as is exampled by this. The 3 times 0 goes away. E to the 3 times 0 is 1, though. Which means that we have 1 equals 2/3 plus c. So c is equal to 1/3, which we can then plug in. This will give us the particular solution. So the particular solution will be y equals 2/3 e to the 3t minus 3t plus 1/3. So this was the general solution. And then this is the particular solution. And it's called that because this is the solution which has this particular initial condition. And typically your goal is going to be to find this particular solution. Ooh, drop that pen, but that is all right. And that just about brings us to the end of today's lesson on antiderivatives. But before we go back and review everything, I just want to point this one thing out, this note. Everything in medicine and biology can be modeled by differential equations. And so this pure time differential equation, this is kind of the introduction to the idea of differential equations. Everything in medicine and biology can be modeled using them because everything in the universe can be modeled by differential equations. Literally everything. Anything that grows or changes, it can be modeled based on differential equations. And so if you're going to be doing any type of heavy research, you're probably going to be developing differential models. If you're going to be trying to model flow rates, if you're going to be trying to figure out how blood moves in circulatory systems, if you're going to be trying to figure out how a chemical compound changes, it's all differential equations. And so all of the stuff that we've seen up to this point is kind of leading you towards this idea of differential equations. Antiderivatives are the tool which you use to solve differential equations. And once we get to chapter 7 is entirely differential equations. And chapter 10 is also entirely differential equations. We'll be doing chapter 7 this semester, and chapter 10 is saved for Math 356. But those are really the big subjects which we want to make sure that you are learning the fundamentals of. And that's antiderivatives for you. We'll talk more about that later. Today, we just focused on antiderivatives, also known as indefinite integrals. We started out with the basic definitions and the analogy about Fred Astaire and Ginger Rogers. We talked about the notation, and then we just did a bunch of problems because I feel like that's the best strategy for beginning to learn these. Honestly, I would not recommend memorizing formulas for the antiderivatives. Instead, I would recommend that you memorize the formulas for derivatives and know them backwards and forwards. Because if you know your derivative formulas backwards, then you know your antiderivative formulas. And so make sure that you feel extremely comfortable with derivatives. And if you feel extremely comfortable with derivatives, then the antiderivatives will be no problem, except when they are, because there's always going to be a few hard ones. We did an rocket science application, and then we talked a bit about pure time differential equations and the idea of differential equations, because when it comes to biology and medicine, differential equations are extremely important. Everything has been leading up to this point. And so it's important for you to get these ideas mastered. And on that note, you have a tremendous amount of homework, as always. And so I will let you get to it. Study and work hard, and good luck with everything.